For this lesson, we're going to be continuing to talk about amplitude modulation. Now, in the last lesson, we talked about amplitude modulation as far as why is it used and the typical applications it's used for, as well as the terms that overlap. For example, input signal, information signal, intelligent signal, audio signal, and most importantly, envelope. And for this lesson, we're going to go over more detail of how to calculate amplitude modulation. A very important fact about amplitude modulation are the sidebands. There's an upper and lower sideband. The upper sideband is the band of frequencies produced in a modulator from the creation of a sum of frequencies between the carrier and the input signal. And the lower sideband is the same thing, just the differences of frequencies between the carrier and input signal. And we have an illustration below that kind of represents how it would look on a spectrum analyzer. You would see the carrier wave be the tip of the spike, and then you have the lower and upper sideband be the sides of it. And we're going to go over more of how to calculate the upper and lower sideband. Now, to provide a little bit more visual representation of how the sidebands look, now we talked about in a spectrum analyzer, we have one of our illustrations below where it has the carrier surrounded by the upper and lower sideband. Well, if you do the modulation index times the voltage of the carrier divided by 2, that'll give you the voltage of the upper and lower sidebands. And notice how it correlates to the AM waveform equation below. So when you see that long equation, that's what it means. It means the carrier plus the lower sideband minus the upper sideband. Also, something to be aware of is how to calculate the bandwidth. The lower sideband and the upper sideband, that range of frequencies is your total bandwidth. And we're going to go over that in a practice problem later on. In a previous slide, I talked about modulation index. Well, that correlates to percentage modulation. And percentage modulation is the measurement of the extent of which a carrier voltage is varied by the intelligence for an AM system. Okay, what that means is if you look at the illustration below, you can see where the carrier starts and stops and the intelligent signal starts and stops as far as its peaks. And by knowing those peak voltages, you can determine the modulation index. And it's also known as the modulation factor, and it's usually a decimal point. And if you multiply it times 100, you get the percentage modulation. And the equations you see to the right, those are very important equations to be aware of and something to take note of. And we're going to go over one of those in a practice problem. Now, to provide a little bit more visual representation of percentage modulation, if you look in the illustrations below, we have 3 different representations of different percentage modulations. For example, our slide all the way to the left, or our illustration to the left, shows the waveforms with 100% modulation. That is an ideal or an optimal modulation signal. The middle picture is an over-modulation signal with over 100%, which means your modulation factor is 1 point something or another, but it's greater than 1.0. And of course, our last picture all the way to the right is under modulation, meaning it's less than 100%. You may see 50%, 66% modulation factor. Again, we'll go over that in a practice problem, but be aware of that's what these images illustrate when you see over-modulation and under-modulation. All right, the very last topic we're going to go over is power content. Now, the modulation factor also affects power. Now, similar to the voltage, if you look at the illustration to the right, your carrier power is just P of C. And then this time we have the modulation factor square times the power of the carrier divided by 4. This kind of mimics how the voltage looks in the previous slides. Now, the equations to your left are very important equations. We have how to calculate your total power transmitted with your lower sideband, upper sideband, and carrier. And we're going to go over that in a practice problem. For this one, we're going to try to tear apart this AM waveform and see if we can fill in this one equation we have at the top. This is the AM waveform equation. We're going to see if we can fill it in just with what we see here. And by filling it in, I mean we're going to determine the modulation index, as well as see if we can determine the frequencies and everything else. That way you can understand how to get from here to there. All right, so let's go ahead and see what we can find. Well, as we talked about in a previous slide, by using the equation to the side, we can determine our modulation index by using our voltage over input over our voltage over carrier, or B minus A and B plus A. All right, so what's B? B is from this point all the way down to this point. So that peak-to-peak voltage, that's B, from the top to the bottom of the maximum peaks, I guess you could say. All right, so that's where B is. Now B, if we want to count it off, let's see, negative 2.5 right there. Let's see, draw that out. Going all the way up to 2.5. So that has a peak to peak, excuse me, of 5 volts. Okay, so B would be 5. I'll draw that right there. All right. Now A would be this point to this point, the lowest peak to peak points. That's A. So looking at this, well, looks like 0.5 and 0.5, that's 1. So A equals 1. And we can plug and chug that in our equation over here. So M equals 5 minus 1 over 5 plus 1. That's going to give us obviously 4 over 6, which is going to give us an answer of, tell you what, move it right down there. That's going to be 0.666 repeating, of course. And I'll tell you what, put a dash on top. Now the other way to find it is VI over VC. Over that way you know how to use that formula as well. Okay, VI is, let's see, right now we have 1, 2, 3, 4. So right there, that line right there, going from here to here, that's V input. So if you took actually your envelope, which is this curve right here, this outer curve, that's your envelope. If you did from the 0 point all the way to a peak, that's your VI, or your voltage input. In other words, that'd be considered your peak voltage for your input signal or your envelope. Okay. Now you got to do the same thing for your voltage for your carrier. Now the voltage for your carrier would be this point, 0 to the 1.5. So it would be from here to here. That's V of C. So that'd be the very center of your AM waveform to actually the center of your envelope. That's the easy way to do it. If you can find the center of where your envelope is, from there all the way to 0, that's your voltage for your carrier. So that's the easy way of doing it. So let's count it up. So we have from 0 all the way to 1.5, so VC equals 1.5. And then we have 1.5 to 2.5, that's 1 for VI, so VI equals 1. And then obviously if we plug and chug that in our equation here, let's see, VI is 1 over 1.5, and it's going to give us obviously same answer, 0.666 repeating. So that way you know how to do it with both equations now, so if you're unsure of one, all you got to know is the other. That makes sense. Well, now we have M. So now we have that guy right there. We have VC, because we just talked about that. It's right there. And now we need to find frequencies. All right. So like we talked about, this upper curve or this curve on the outside of the waveform, that's your envelope. That is your frequency of your input. So that is just knowing how to read an oscilloscope just like you normally do. So I want to pick a point right here. So we're going to say from here to here is 1 full cycle. Because if you look, it starts right here, ends right here. They're both the exact same waveforms. So 1.5 and 3.5, that's 2 milliseconds. So our frequency for, and it's F of A, by the way, because like we talked about, there's F of I and F of A. They're both the same thing. So we'll go down here. So the time, so I'll say time for A is 2 milliseconds. Well, like we talked about in our previous lessons, if you want to find frequency, it's 1 over time. So frequency equals 1 over t. And that equals 1 over 2 milliseconds. And that's going to give us an answer of once you plug in and chug in calculator. Should give us 500 hertz. Okay, so our F of A is 500 hertz. That was an easy one. Now let's see if we can find our frequency of our carrier. I'm going to do the same thing. I'm going to go from 1.5 to 3.5 milliseconds because since that's one cycle over here and I know that's 2 milliseconds, let's see if I can count how many cycles it goes through. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I just went through 20 cycles in 2 milliseconds. So that's 20 divided by 2 milliseconds. Let's go and give me an answer of 10 kilohertz. So I did that instead of just trying to count up one cycle and try to determine, okay, this cycle starts here, ends there, and try to guess. Just using logic, I said, okay, I know I have 20 cycles from here to here. I know it's this amount of time. So right then there, I was able to find the amount of cycles for the amount of time and then do my math. So my carrier, f of c, is 10 kilohertz. Let's see if I can make some room. Tell you what, I'm going to pull off to the side here. Let's see. So V equals V of C. Well, we know V of C is 1.5 because we talked about that earlier, from the center all the way to the start or the center of the input voltage is 1.5. So we know that one's 1.5 sine 2 pi f of C, which is 10 kilohertz. Please excuse my handwriting, and I'll just put T right there. Plus, now the modulation index times the voltage of the carrier divided by 2. So I'll just put it in there. I'll say 0.666. I have to go for a sharper pen on this one. All right, carrier voltage is 1.5 divided by 2. And then that's going to be cosine 2 pi. And this one's going to be the carrier minus the input frequency. So that's going to be 10,000 minus 500, and that's T. And of course the other one's going to be the exact same thing, which I'm not going to write quite yet. I'm going to go down and rewrite the equation again, but I'm going to do it by solving this one equation right here, which is pretty simple. So we have voltage equals 1.5 sine 2 pi 10 kilohertz time plus, and I plug and chug that in my calculator, is going to give me 0.5 cosine 2 pi. And for this one, I'm going to plug and chug that in my calculator as well. 10,000 minus 500, 9,500 hertz. And time again, minus. Now for this one, it's going to be adding those two together. So it's going to be 0.5 cosine times 2 pi. And then we're going to add those two together. So it's going to be 10.5 kilohertz and then T. So we're able to go from waveform to the equation down below and able to fill all that out. And we're able to do it by reading the oscilloscope and using the equations provided. So right there is our final answer. So I think that was pretty simple. All right, let's go on to another problem, hopefully an easier one. All right, for this example, hopefully it's not as daunting as the last one. All right, so we have the AM frequency range is between 540 kilohertz to 1600 kilohertz. How many broadcast stations can be established using the following diagram below? Okay, this is where you need to find the bandwidth of each AM broadcast here. Over what we know. Down here, we talked about where the lower sideband is the carrier frequency minus the input frequency. And then this one's obviously the carrier. And this one is the carrier frequency plus the input frequency. All right, so that's pretty simple. The total bandwidth for this particular broadcast. So looking at this, we have 541 and 539. Well, it has to go from here to here, which means you have to use the frequencies between 539 and 541. So the differences between those two would be 541 minus 539 is going to give you 2 kilohertz. Does that make sense? Because you went this direction, 1 kilo, and then you went that direction, 1 kilo. So you went both directions by 1 kilohertz. So by adding those together, you have a bandwidth. This whole thing right here is your bandwidth, and it's 2 kilohertz. And then we went over that a little bit in the slide, or at least we showed an image of it. Now we need to establish how many of these we can fit in the range of 540 kilohertz to 1600 kilohertz. All right, so we just need to find the difference of those two. So 1600 kilohertz minus 540 kilohertz. And my handwriting is not up to par today. It's going to be 1,600, or excuse me, 1,060 kilohertz. Or in this case, we have 1.06 megahertz. But we'll keep it in kilo, just keep it simple. Okay, so if we have a whole AM range, if this right here was the whole AM range, you have a range of 1,060 kilohertz. And each AM broadcast is approximately 2 kilohertz. So, in other words, you'd have a spike there, spike there, spike there. So if you had this on a spectral analyzer, you can get several broadcast stations out there. That's 2 kilohertz each. So find the amount you can put in this one little range. It's going to be your range divided by bandwidth. And again, very simple one. Plug and chug that in your calculator. You can get 530 stations. So that would be your answer. So you'd be able to see 530 spikes going up and down this range of all your AM broadcast stations. So this one was relatively easy, but I just want to go over of how this would look if you're trying to determine the bandwidth and correlation of the AM range here. Tell you what, let's do one more example problem. All right, looks like we got ourselves a power content example here. All right, the modulation percentage is 80%, and a power at the carrier frequency is 500 watts. Determine the total power transmitted of the AM signal. Okay, that's pretty simple. Now, if we looked at one of our previous slides, I showed you a diagram that looks similar to this. I had the lower sideband and then the upper sideband, and then that doesn't even look like a B, and obviously the carrier. Well, the carrier has a power of 500 watts. And this one's unknown, and this one's unknown for now. So in that same picture, I had something that looked like this. I had the modulation index times the power of the carrier divided by 4. And I had that for both sides. Okay, so we want to find the total power transmitted. So we're looking for that guy. Now the good news is, I think we're able to use both of these equations to find the answer. So I'll tell you what, let's try this bottom one right here. So I have the modulation index. Since we know capital M is the percentage, which is 80%, if you actually want to make this modulation index, it's supposed to be a factor, so it's 0.80. All you do is just move the decimal point over. Okay, well, so if we want to put this in the equation, it's going to look something like this. It's going to be P of T equals 500 watts. Again, I'm using this guy. 0.8, that's going to be square, divided by 4, and then the same thing again, 500 times 0.8 squared, divided by 4, and then plus your 500 watts. So if we plug this in our calculator, it's going to look like this. P of T equals 80 plus 80 plus 500. And that'll give us a final answer of 660 watts. Okay, that was pretty simple. And that was using that equation. Let's use the other one since we got time. So P of T equals 500 watts. Then it's 1 plus modulation index is 0.8 square, divide by 2. And plug and chug that one in our calculator as well. It's going to be 1 plus 0.32 times 500. So it's going to give us an answer of 660 watts. So the good news is both the equations work just fine, and we're able to find them very quickly. So I know this is a very easy problem, but I want to go over how it would look like if you want to use just power with our modulation percentage. Hopefully I gave you enough information here to be dangerous, and I hope you all have a good evening.